Here we are, chapter 11, part 2. So last time we talked about the shuttles themselves, so getting the NADH into the mitochondria to where they need to be able to take part in the electron transport chain. And now we're going to talk about the electron transport chain itself. So the electrons are transported through a series of membrane-bound carrier system, called the respiratory chain. So the electron carriers in the respiratory chain are NADH, ubiquinone or coenzyme Q, and cytochromes, cytochrome A, B, and C. So the electron carriers. So the components of the respiratory chain are arranged in order of increasing redox potential. Okay? So those components of the respiratory chain are arranged in order of increasing redox potential. Increasing redox potential. Let's find a good definition for what redox potential is. So redox potential is a measure of the ease with which a molecule will accept electrons, which means that the more positive the redox potential, the more readily a molecule is reduced. So as we go down the line from NADH to coenzyme Q and to our different cytochromes, they are more and more willing to accept an electron. Okay? So hydrogen or electrons flow through the chain instead. So we're going to just take out this part. I don't like the wording on that. We're going to talk about electrons throughout this. Electrons flow through the chain in steps from the more electronegative components to the more electropositive oxygen. So the order of the carriers: NADH goes to that coenzyme Q or ubiquinone, goes to cytokine B, cytokine C1, cytokine C, cytokine A, cytokine A3, and finally to oxygen or O2. This right here, this order, will be a question on your exam. So take a look at that and make sure that you have that down. The respiratory chain collects and oxidizes reducing equivalents. So the reoxidation of NADH and FADH2 in mitochondria by the electron transport chain reactions, or that flow of electrons through a series of redox carriers, finally reduces O2 to H2O. Remember that redox reactions, that loss of electron is oxidation, gain of electrons is reduction. So our oil rig. The sequence of electron transport. So there are a series of 4 protein complexes arranged from lower to higher redox potential. Complex 1, complex 2, complex 3, and complex 4. We keep it a little simple with that. Now, this right here is kind of a big old mess. So we're going to draw it out a little bit simpler. So we're going to use this as our base, but we're going to draw it a little bit easier to understand. Okay, so first things first, we have our membrane. So this right here, remember, this is our inner, this is our inner mitochondrial membrane. This side down here is our matrix, and this is our membrane space. Sweet. So we're going to start off this whole process talking about something called complex 1. Okay. So complex 1. Complex 1, also known, we'll see it, the name, it's an NADH dehydrogenase. So it is also known as NADH dehydrogenase or NADH reductase. So these are all AKAs. NADH dehydrogenase, NADH reductase. Complex 1 drives proton transport endergonically. Remember, endergonically. Think endergonic. Endergonic means that it absorbs energy from the matrix to the intermembrane space. So it's going to drive proton transport, so it moves hydrogens from the matrix up to the intermembrane space. So it's going to oxidize NADH by CoQ, and CoQ is reduced. The reduced CoQ is a mobile electron carrier, and it transports the electrons obtained from the NADH to complex 3. So let's make this make a little bit more sense. So we talked just before that whole process, those different shuttles and everything, its whole job was to get us having NADH here inside the matrix. Complex 1, its job is to break apart this right here and take those electrons, let's use purple for the electrons, take these electrons away and pass them along the shuttle. So the NADH dehydrogenase is going to break this apart. Let's do green. It's going to break this apart right here so that we end up with NAD plus and a hydrogen ion. And it's going to take those electrons and pass them to a transporter called CoQ. Okay. That CoQ, also called coenzyme Q, or ubiquinone, or ubiquinone, depending on how you want to pronounce it. Okay, so whenever we see coenzyme Q or ubiquinone, it means the same thing. I think the difference in name has to do like whether it has the electrons or not. Don't worry too much about that. Just understand that coenzyme Q and ubiquinone are essentially the exact same thing. Now, coenzyme Q is a transporter. So it is literally going to move through the membrane over to complex 3. Okay? We will get to complex 2 in a moment. It's a little bit difficult to draw with the mouse. I'm still getting used to it. So that CoQ, or the coenzyme Q ubiquinon, is going to transport these electrons to the complex 3. When that happens, right here, our complex 1, it also has this little tunnel. So when it gets electrons, when the electrons are here on the complex 1, that increases the energy that it has in complex 1, and it actually will open this tunnel. And these hydrogens that are now free floating, we're going to get some of those and pump them up out through into that intermembrane space. So they go from the matrix up into the intermembrane space to start building that gradient that we need eventually to form ATP. So our coenzyme Q then gets those electrons and passes them to our complex number 3. Well, let's talk about that. So complex 3 oxidizes CoQ. So just think about it like oxidizes, meaning that it loses electrons. So the CoQ passes the electrons over to complex 3. And it does this with cytochrome C. So the electrons get transported from CoQ to cytochrome C. And that was our next step here. So we have from our NADH, goes to our Q. Hold up. Let's see, we'll break this down. We're kind of skipping these 2 steps and going straight to over here. But we'll break this down a little bit better and talk about these, because these are part of complex 3. So complex 3, so it essentially so complex 3's job is to transport the electrons from coenzyme Q to the cytochrome C. Complex 3 also drives proton transport to the mitochondrial intermembrane space, and complex 3 receives electron pairs from CoQ and delivers to another mobile electron transporter, cytochrome C. So what actually happens, a little bit more detail here, is that our cytochrome B and cytochrome C1, both of those are part of our complex 3. So cytochrome B and cytochrome C1, they're part of it. They're going to take the electrons, pass them to each other, and then pass it along to cytochrome C. So we go from complex 1 to CoQ, and we pump up hydrogen through complex 1. Coenzyme Q brings it over to complex 3, and cytochrome B and cytochrome C1 are both part of complex 3. They pass the electrons, and then pass it on to cytochrome C. And then during that process, more of these hydrogens that are here in the matrix are coming up through and getting pumped into the intermembrane space. But we're going to do a quick pause because we jumped straight from 1 to 3. What about complex 2? Complex 2 remember we talked about NADH here, but we have something else that we made besides NADH. We also made FADH2. So we have a complex 2 in between. Except you'll notice the difference between these complex 1 and complex 3 from complex 2 is that complex 2 doesn't go all the way through the membrane. It does not have a channel to pump hydrogens through. So complex 2's job, FADH2, its job is to oxidize the FADH2 to also put electrons and bring electrons up. So it takes the electrons from here, breaks apart this bond, and then we get FAD and hydrogens out and about. These hydrogens also get pumped up through. So it's going to pass those electrons up to the CoQ as well and follow the same path and makes it to our complex 3. So complex 2 also drives protein transport from the matrix to the intermembrane space, and CoQ receives electron pair from FADH2 and transports to complex 3. That sounds a little bit worded incorrectly. I would ignore this part here. I don't know if that's a typo or if it's just worded weird, but complex 2 does not actively transport hydrogen through. The release of the hydrogen helps pump up through, but as we can see here, it does not bring hydrogen straight across. We know that the CoQ, though, receives the electron pair from the FADH and transports it to complex 3. And also, if we think back to the last video, talking about the shuttles, the glycerophosphate shuttle, we talked about how it takes those electrons and converts them directly to FADH2, and then it passes them off directly to CoQ. So we could also throw a little note in here that our glycerophosphate shuttle is also putting electrons in right there to help it to continue that chain. Okay. So now we have electrons at our cytochrome C. We're right here in this process, cytochrome C. Cytochrome C is going to pass along and move those electrons and pass it along to complex 4. Complex 4 receives the pair of electrons from cytochrome C and also drives proton transport to the intermembrane space. Complex 4 also driving these hydrogens, whatever the hydrogens there are, driving them up into the intermembrane space. using the energy from those electrons. Finally, complex 4. Within complex 4, we have 2 more cytochromes. Cytochrome A and cytochrome A3. And if we look at our process from cytochrome C to cytochrome A and cytochrome A3. So in all actuality, we can really rewrite this whole process. NADH goes to CoQ, which goes to complex 3, which contains cytochrome B and cytochrome C1, which then goes to cytochrome C, which goes to complex 4, which has cytochrome A and cytochrome A3 as part of it. And our last step to oxygen. So finally the electrons, this cytochrome A to the cytochrome A3. And here comes our lovely oxygen molecules, and it dumps off those electrons to that oxygen, and they're going to get a couple of hydrogens that are still here in the matrix attached to them, and we have a beautiful H2O in the end. So our oxygen gets those 2 electrons, gets two of the hydrogen ions from inside of the mitochondrial matrix, and we get H2O. So just this last note, this finally complex 4 transfers the electron pair via the cytochromes AA3 to oxygen producing water. This enzyme is also known as succinate dehydrogenase. So within here, you have a lot of these names of the enzymes of like CoQ, CYP, oxidoreductase, succinate dehydrogenase, succinate CoQ oxidoreductase, all this sort of stuff. In all reality, rather than trying to memorize each and every single one of these enzymes, look at the name and make a relationship to what it's actually doing. So for example, the CoQ CYP oxidoreductase, aka complex 3, so that's another name for complex 3. What's complex 3's job? It's to help oxidize. It oxidizes CoQ in order to reduce CYP. Hopefully that makes a little bit of sense. Where complex 3, this whole thing, it's an enzyme whose function is to take electrons from the CoQ to then give the electrons to the cytochrome C. And that's exactly what its whole name is saying. So if you understand the process, you will much easier be able to understand the names, the extra, like the fancy biochemistry names that you'll see on here. Okay. What else we got? Okay. Finally, so we've done all of this, right? All of this stuff to this point. But we still haven't made any ATP. No ATP has been made yet. Oh, let's used to do it. Oh, let's just do this. Here we go. Move it over. There we go. So we still haven't made any ATP. That's coming. So this whole process, right, was to help us get all of these hydrogens, to get a whole bunch of hydrogen. All the way up in this space. So now we have a ton of hydrogens. Up here we have a gradient. And finally is going to come our payoff for all of that work. So now we've officially created that generation of electrochemical proton gradient. So during electron transport, protons, those hydrogens, are pumped out from the matrix to the inner mitochondrial membrane. This should say, the better way to word this is during electron transport, proteins are pumped out from the matrix through the inner mitochondrial membrane into the intermembrane space. That's a better way to say that. So this endergonic extrusion of protons from the mitochondrial matrix to the intermembrane space generates a proton, or an electrochemical gradient. Now, exergonic return of these hydrogens to the matrix is going to power our ATP synthesis. So the passage of 3 hydrogens is required to synthesize one single ATP. Which, if we back up, we can actually now see and understand where we got those numbers from, where we kind of get those numbers from when we talk about the amount of ATP produced by each. So if we see NADH, with one NADH we get about 4 hydrogens pumped out here. And then we see 4 and 2 here, but remember that now that's including our FADH. So we can roughly say that anywhere between 4, 5, 6, maybe like 7, 8-ish, 7 or 8 of these hydrogens is coming from each of these NADH. And then 2, 3, maybe 3 or maybe 4 are coming from the FAD. Again, these aren't like exact values, but we can start to kind of see why we have that NADH is producing 2.5 ATP, and the FAD is producing 1.5 per FADH2. Just a cool little connection there. So now we get to something, fancy name, called the chemiosmotic model. So the chemiosmotic hypothesis, now this is putting a nice little bow on everything. This is giving us kind of the name of the model for this whole process that's occurring in order to form ATP. So this model, or this hypothesis states, as the pair of electrons flow through the electron transport chain, protons generated from the reoxidation of the reducing agents are ejected endergonically from the mitochondrial matrix, or the N side, to the intermembrane space, called the P side, of the mitochondria. This results in accumulation of protons in the P side, so increase of protons in the intermembranous space, leaving the N side more negative, and generates a proton gradient across this membrane Or we can say this generates a pH gradient or chemiosmotic pressure. That's that word, chemiosmotic pressure, due to differences in protein concentrations across the membrane. This mechanism stores the energy of electron transport in an electrochemical potential. So that gradient that we've created is essentially a storage of energy. Because if once there's an opportunity for that gradient, for those hydrogens to pass back through, that movement and all that stuff is going to release a bunch of energy as it occurs. As the chemical potential across the membrane crosses a threshold value, the protons are pumped back exergonically to the matrix via an F0 subunit of complex 5, which is known as the ATPase or proton ATPase, hydrogen ATPase, or ATP synthase. Most often you will see it as ATP synthase. However, understand that all of these ATPase, proton ATPase, hydrogen ATPase, all of these are acceptable names for it, but most commonly it will be referred to as ATP synthase. This is an energetically favorable process that drives ATP synthesis. So that ATP synthase contains two major units. F0, which is oligomycin sensitive. In other words, it's blocked by the antibiotic oligomycin and thereby blocks the exergonic return of the protons back to the matrix. And the second unit is F1, which is composed of a few more subunits and actually responsible for ATP biosynthesis from ADP and phosphorus ion. With this, this is a little bit of extra information. What I would pick out of this little chunk right here is understanding that I would make sure the antibiotic oligomycin is going to block ATP synthase, and that the second unit, F1, is what is actually responsible for ATP biosynthesis from ADP and phosphorus ions. I would pull out those two chunks from that little section there. Make sure you know those two things. So the return of protons through the F0 unit starts the motor of F1 unit that starts rotating while condensing ADP and the phosphorus ions to generate ATP. The coupling of electron transport that generates this chemical potential and synthesizes ATP in the respiratory chain is the basis of chemiosmotic hypothesis. So that was a lot of words to basically say hydrogen gets pumped from the matrix to the intermembrane space, and once we get enough of them, it's going to flow through what's called complex 5, aka ATP synthase. So this is complex 5 or ATP synthase. So all of these hydrogens, a whole bunch of these hydrogens, all of these guys are going to flow straight down through. Hopefully, sorry for that whistle. Got picked up really aggressively. Sorry. As the hydrogen moves through this channel, you can kind of think like inside of this channel, there's almost like a turbine, you could call it, that as the hydrogens flow through, it makes it rotate. So it's turning that potential energy into actual like movement energy. So it's actually moving. And that spinning, the spinning inside of here, so like this is the like a little rod, and there's like a little turbine right here, right? So this starts to spin, which then you think like attaches to another little motor here, which causes this to get energy, which actually combines the ADP and the phosphorus and makes ATP. So the movement of the hydrogen causes the ATP synthase in here to spin and drives that motor, and that motor uses that energy to produce ATP. That's what all of this just said. So, that oxidative phosphorylation forms ATP. Thus, chemiosmotic hypothesis describes coupling of electrochemical gradient to ATP synthesis. So, making that hydrogen gradient in order to produce ATP. So, that ATP synthase, aka, all of our good stuff, uses the free energy of the electrochemical hydrogen gradient to form ATP. Now, we also have a couple of uncouplers of the oxidative phosphorylation. 2,4-dinetriphenol and carbonyl cyanide p-trifluoromethoxyphenylhydrazone, or FCCP, just no FCCP, are two examples of uncouplers between electron transport and oxidative phosphorylation. If you remember, recognize this, cyanide. Cyanide's a poison. Use of these blockers can stop ATP biosynthesis, but do not interrupt electron flow through the electron transport chain. So these are the essentially poisons, where if you take these FCCP or 2,4-dinotriphenol, so cyanide, what cyanide actually does is it injects itself into that ATP synthase. So like all of this still happens, but now we're just not forming ATP. And if ATP is unable to be formed, the tissue does not have energy. It doesn't have energy to perform any of its other tasks, and the tissue will actually die. And that's what cyanide does. It stops the production of ATP and kills you. Brown adipose tissue in newborns. So I want you to pay attention really close to this, because there will be questions on this on your exam. At least one or two from what I recall. Brown adipose tissue in newborn humans contains large numbers of mitochondria and also high in cytochrome levels. This tissue continues to oxidize fuels, but do not synthesize ATP because mitochondria in this tissue does not couple the electron flow with oxidative phosphorylation. However, this produces heat. Brown adipose tissue contains a special protein known as thermogenin, which acts as an uncoupler protein. This protein provides a different path for protons to be transported into the mitochondrial matrix without passing them through the ATP synthase. Thus, although the energy of oxidation is not coupled to ATP synthesis, the exergonic flow of proton is dissipated as heat and maintains body temperature. So in babies and newborns, they need to be able to keep their body temperature up. Newborns tend to run a little bit warmer than adults or than older people. And this is the reason why. So in the brown adipose tissue, that protein thermogenin acts as an uncoupler, so it stops the ATP synthase to let the body, remember we were talking about how the moving of the hydrogen up is endergonic, and then when it all comes back through, it's exergonic. So we're creating and having that exergonic reaction occur, so we have more exergonic to produce heat in order to keep up body temperature as a baby. And that is the brown adipose tissue, what happens inside of there. I'm going to jump back really quick to this little chunk because I skipped over it. This is a little tidbit of extra info. There will be 1 or 2 questions that come from this little chunk. Just understanding the different names of stuff, and like what blocks what. So rotonin, antimyosin A, cyanide, and carbon monoxide are blockers of the electron transport chain. Rotonin blocks the electron transport chain between NADH to CoQ. Antimyosin A, think about it. Antimyosin A blocks the electron transport chain between cytochrome B to cytochrome C1. So that's within what complex? It's within complex 3. And then the cyanide ion and carbon monoxide block the electron transport between cytochrome A and A3 to oxygen, so it stops it right there. Of these, most likely you'll get asked about cyanide or carbon monoxide, most likely, but I would still recommend knowing these 2 as well, and just where they block, because decently easy enough thing to remember, and should be free points if that specific question gets asked on the test. Okay, that was the end of chapter 11. Chapter 11 is a little bit information dense. Hopefully this video helps you guys, and next time we will move on to chapter 12. Thank you, and study hard, and have a great day.